Exactly, that's what I said. So I said so using course and you can use your personal laptop. And I tried to guide it, take stuff measure, so it's like, okay, so I'm taking this out, it's not better outcome, but
I'm getting older, I know, this is hard to believe, but
they're weird. Like, apparently I would just set a bench and then I put citizens bench and set up like my forehead right here. And then I just like support myself with my arms. Stay not becoming too much. Knees are bent. Barely put my hands in the ground, just support a little bit and try to support as much weight as possible on my neck and then just hold there for 20 seconds. Neck and those two.
Wait, so, oh, in the gym, okay, okay.
It's the same thing on my phone. Like, I don't think my I don't know if Mike Tyson ever did them, but probably. I don't have like any of the equipment to actually do it. So yeah,
Oh,
Okay, great. Thanks for coming. This is our second pizza seminar. I'm so happy to see such a big crowd. I hope we can keep this up for all the future pizza seminars. We may even diversify from pizza to something else in the future. So keep your eyes peeled for that. You can also give me suggestions, and we can maybe even think of other foods. Okay, I'd like to introduce our speaker. Graeme is here to speak on the analysis and visualization of large binary data sets. Take it away, Graeme.
All right. Todd said, my name is Graeme Sweet. I am the son of Lowell Sweet, who is over in the corner, who is a professor here for 40 years in mathematics. And it's great to see him here, and a bunch of my old professors showed up here, which is wonderful to see too. So I want to be upfront. I basically started a little computer company. And I'm going to be talking mostly about the software that I have developed for this company and basically how it came into being, why it came into being, what's necessary. So the Sweetscape software started way back 2001 and released a software called, now it looks like 010 editor. I like to call it 010 editor. I kind of chose that name because I liked the name 010 editor, but nobody knows that it's called that. But I call it 010 editor. If you want to call it 010, go ahead. I don't really care. You can call it whatever you want to. The websites are up there, sweetscape.com, 010editor.com. If you ever want to email me after the presentation with any questions, feel free. I'm always happy to take questions. The software has gone kind of around the world. It's really neat to see. It's about, last guess, about 140 countries around the world, which is kind of neat. You're seeing places like Antarctica and, Christmas Island and these little things. You're kind of collecting all these little places around the world. Number of customers, I don't know if I should say exactly, but we're talking, 5 figures. If you're talking, people who have it, who didn't quite exactly pay for it, you might be into 6 figures. I won't say too much about those people. And the prices are listed there. I give a pretty good academic discount. And this is Windows, Linux, and Mac written. I'm kind of a C++ guy. I'm kind of C++. Kind of zealot, I guess. I don't like other languages. I'm probably the old fogey guy, shaking my cane out the other people running those newfangled languages. But I'm still running C++. Now, I didn't want to make this kind of like a marketing seminar where I'm trying to sell software. I kind of felt bad, but I still wanted to come back to my university where I started off with and kind of give something back and hopefully inspire people about how interesting this is. So I figured I would incorporate a little game into this presentation, and I'm going to have some questions as I'm going through the seminar. And if you get a question right, I'm going to say you can have the free software for free if you want. So it's a little game, and at the end of the day, if you didn't answer any questions right and you still want a free copy, still email me. So it's kind of like the kids' soccer trophies where everybody gets a trophy. So everybody kind of wins. So we'll call it a game. So we'll start off. So first question, the name of the company was Sweetscape Software. Now, Sweet is my last name. Does anyone know where scape comes from? Any ideas? Yes.
Scape is kind of a general topic for defining an environment.
Yeah, that's where okay. So more narrowed down, it came from a piece of software. Another piece of software that had scape in its name. It's an old piece of software, Netscape, very good. Free software to this guy right here. Anyone tell me what happened to Netscape? Netscape died. Anyone know why briefly? So basically Netscape, they thought it was so good that they didn't have to work on it anymore. And I think that's a common lesson that you've got to learn in computer science. If you get to the point that your software you think is so good, I'm not going to work on it anymore, you quickly get overrun by someone else. So I'm trying to keep working on this, trying to keep going, trying to make it better. And right now, I think this is probably the best text editor in the world. That's what I market it as. And it's gone all around the world. I can't list actual companies who have bought it, but I can tell you kind of areas that have bought it. For example, Major operating system developers have bought it. That's a clue. Major CPU manufacturers have bought it. Major intelligence all around the world have bought it. Military, there's just a huge swath. It's a huge gaming, cybersecurity. It's really neat to see just all the different depth. So I want to get into what the software does, and this is kind of the outline of the talk. I want to introduce you to binary data. I want to do a brief introduction to hex editing and why it's sometimes not very useful, and then I want to get into something that is more useful, which allows us to understand binary data, which is binary templates, and I'm going to do a little section on visualization at the end, and that's not very big. So my background, I went to the rural. I grew up here in PEI in Sherwood. I started UPEI 1994. Now, little story. A couple months ago, I went into a restaurant to pick up takeout, and I was talking to the nice lady at the desk, and found out that she went to UPEI too, or she went to UPEI, and she asked me, and I told her that I went to UPEI as well, and she said, "Oh, what year did you go there?" And I said, "Gee, that was back in 1994 I started," and her response was, "Oh, I wasn't born then." And I don't think I've ever felt so old in my life. And I realize there's probably quite a few people who weren't born in 1994. But if someone asks you that question, the correct answer is not. I was not born then. So I went through, and I only did 2 years here at UPEI because they only had 2 years of computer science. So then I had to switch to another university to finish off my degree. And I ended up going to McMaster University up in Hamilton, Ontario, and did 3rd and 4th year up there, and managed to graduate top of my class in computer science up there. So if you have any qualms about whether someone from UPEI can compete with some of the bigger universities in Ontario, I think you can be fairly secure that UPEI's got a really good quality instruction staff here. Some of the best professors I had were at UPEI, and some of them are in this room, which is great to see. So when I graduated McMaster, one of my loves was computer graphics, and I really loved OpenGL. I don't know if anybody still uses OpenGL these days. Is that still alive even? It's changed so much. So I went into something called, I wanted to go into computer graphics, but there wasn't something exactly. I found a supervisor at UNB who did human-computer interaction, which is basically computer graphics, but you do experiments on people as well, okay? So you basically make a nice computer graphic, and then you get people in, and you get them to do some experiment with it and tell how well they can understand, and you do a bunch of statistics on it, and that was kind of my master's. So after that, I got hooked up with a company that was started by my supervisor, and they actually had an ocean visualization lab in UNB. And if you can figure out why they have an ocean visualization lab in Fredericton, New Brunswick, I will be impressed, because I've never figured that out to this day. So I worked there, and by the way, they've actually gotten rid of that. University of New Hampshire came up and bought out all the professors and encouraged them to move down for a lot of money down to New Hampshire. So the Ocean Visualization Center is down there. But there was a software that they came out of the Ocean Visualization software called Fledermaus. And I started working for this company. It was called IVS when I was working there. It's now called QPS. It's been bought out. But Fledermaus was my first introduction to big data, big binary data, and what that means. I didn't really have kind of a grasp of what that was when I was going through university, but I soon kind of gained an understanding of what that meant. Let's see. Oh, and then I guess I should mention, way back in UNB, I did have kind of an interest in, some of these old games. Doom was big when I was going through. I remember I would open the old, computer labs where we would sneak Doom onto some of the computers and play them. And some of these games you could go in and you could edit some of their save game files if you knew how to do hex editing. So I kind of figured that out. So I had kind of interested, and I was kind of writing my own hex editor just kind of on the side, but never really did anything because, there's a whole bunch of hex editors. And don't worry, I'll explain much more about what a hex editor is later on. So while I was at Fledermaus, just kind of on a side thing, I started the software O&O editor. Put it up online, and it just started slowly growing until it was finally enough for me to kind of take a leap and do it full time. All right. So what is binary data? You've probably all seen when somebody sends you some kind of attachment and you open it up in Notepad and it looks like this, and it's just complete gobbledygook, and you cannot understand anything. This is binary data. Now you can see a little bit of something here. You can see file 001.txt. You can see, but almost all of this is just unrecognizable thing. So this is binary data, and the question is, how do we make sense of this? How do we deal with it? And by the end of this seminar, we're going to show you how to understand that data. All right. So I just want to do a little thing about why binary data, because really there's these great text formats that have come out in the last 10, 20 years, XML, JSON, YAML. It's like, why don't we just always use those? And can I say that often text formats are great and they should be used, and I've seen lots of times where binary formats that have been used that shouldn't have. So I say if you're doing computer science, try to use, open, easy to understand XML formats if you can. But binary has a certain place in the world. Binary is a lot smaller. You can get much more compact data, and it's much faster to be reading. Now, when we're working with Fledermaus, we're working with terabytes of data that would take 2 to 3 days to process. So if you're talking, doubling the size of your data, you're talking, 3 or 4 terabytes. And then if you're doubling your processing time, you're talking 4 and 5 days. So you really have, important processing data on these big data sets. But the problem is with binary is that it's much harder to understand. And that's what we're going to get into. All right. All right, so this is the basics, and this is about as basic as you get. 0 and 1. That is what a computer knows, basically on and off, high voltage, low voltage states. And that is great if you just want to store the numbers in 0 and 1. But what if we want to store the number 2? Well, then we have to put multiple digits of binary together. So here I put a 1 in this place. That means that can equal to 2 decimal. I can put 2 digits together, gets up to 3. If I put 1 in this position, that gets me up to 4. And I keep adding in more and more binary digits together, and that lets me get greater and greater decimal numbers. This is basic binary, and I hope people have seen this before. Binary. So this is, you can represent this kind of mathematically. So if I have a base B and if I have a number and I have a number of digits, from dn all the way down to 0, you've got your first digit times your base to the power of n, dropping down all the way to your last digit times your base to the power of 0. So for example, if we want to deal in octal, which is base 8, then 5,374 in octal will be 5 times 8 to the power of 3 plus 3 times 8 to the power of 2 plus 7 plus times 8 to the power of 1 plus 4 times 8 to the power of 0, and that's 2,812 in decimal. Now, does anyone know there is a place in Linux where octal is used commonly? Do we have any Linux aficionados? There's one place, and people might not even realize that they're using octal there. Anyone know, or you want a hint? It's in the file system. Yes?
Editing file permissions?
Editing file permissions, that's right, okay? chmod, if you do 7, and we know what 744 means? That's your most common. 744 is read write, execute, read, and that's when you're doing chmod. Those are all octal numbers, and most people don't know, so free software. So why do we use, another question, why do we use in everyday life, why do we use base 10 numbers and not base 8? You know, we could be using base 12. Any conjectures? Fingers, it's probably, that's the most likely. Because, yeah, there's nothing special, you know, about base 10. You could really use any base, and this is going to come down and be more important later on. Okay, so now we want to use a different base system, and we're going to go up to base 16. So that means instead of just 10 numbers, we're going to need 16 numbers. So we're going to need to invent 6 new numbers, and we're going to call them A, B, C, D, E, and F. And I don't know if they could have come up with something more original, you know, to use maybe a different symbol or something instead of using letters for numbers, but it works. So we have a new number. The number A is now equal to 10, B 11 all the way down. We have F is equal to 15. And this, you can see it also corresponds. So hex 0, okay. And hex F is 1111. So there's a nice, this is a nice correlation. All right. Now, so we can also do, I just want to make sure people understand kind of how base 16 works, because I'm going to be doing some base 16 works, base 16 numbers through here. So our same formula as before. So if I have 1, A5, 2, 7, that's 1 times 16 to the power 4 plus 10. A is 10 times 16 to the power 3 plus 5 times 16 to the power 2 plus 2, 16 to the power 1 plus C, which is 12. And that's how you convert it back to decimal. So, you know, hex is just another way of representing that decimal number. There's nothing magical about it. So I want to speak about bytes for a second. Now, when you're writing to disk, you never write 1 bit at a time. And when the designers came in, they found it was much easier if you synchronize it so that you're writing a certain number of bits at a time instead of doing 1, 1, 1, 1, 1, 1. So in most systems, we're doing 8 bits. It's 1 byte, and that's kind of our lowest unit of reading. So if you get any kind of file that tells you how many bytes big that file is, and there's no way to read just 1 bit from disk. If I want to read one or modify 1 bit from disk, I've got to read 1 byte, modify that 1 bit, and then write the byte back out. So this is kind of the smallest unit for reading and writing, and we actually do all of our addresses for bytes. So all of our addresses referencing bytes, not bits. Okay, I know that's a little confusing, but we're much more interested in what bytes. Has anyone used any computers with other byte sizes? We use almost all of our modern computers have 8 bits. Is anyone old enough to admit that they have used computers with other bit sizes? No, I'm not that old on it. Does anyone know of any computers that have other byte sizes? Know any? Yes.
There's an old Russian computer that runs on vacuum tubes that was constructed with a 13-bit word. Nobody knows quite why. Probably because that's all the vacuum tubes they could shove into the space. But it had a 13-bit word.
Impressive. There's a PDP computer, which I've never used. I think that was a 12-bit, yeah. And then they've done some other ones. So there's nothing special or magical about 8 bits in a byte, but that's just kind of a standard that we have that everyone likes to do that. Does anyone else get annoyed that some download speeds are in bits and some download speeds are in bytes? Ever say yes if you do that? Yes, okay, that's the right answer. So you guys get free software for doing that. That was an easy question. Okay, And I also just want to mention that all of our addresses when in computer science land are zero-based that I'm going to be using. None of that means 0 is the first element in the array. Anyone know there are some languages that start at 1? Anyone know that? JavaScript, is that annoying? There's Pascal, there's another one. Oh, so annoying when they don't, yeah.
Old Visual Basic.
Old Visual Basic, oh.
Yeah.
Please.
Option base 1.
Please die. Now, why are we using hex in hex editors? Hex has this nice property that every hex digit corresponds exactly to 4 binary bits. So if I have 2 hex characters, 0, 0, that corresponds to actually the 8 bits, 0, 0, 0, 0, 0, 0, 0. If I have FF, that I know that corresponds exactly to 8 ones. And if I have 8, 0, I know that that 8 is that first position. This last one is 0. So if somebody gets good at hex editing, they can just look at the characters and say, oh, I've got an A. I know that that's 1010. Or if they have a C, I know that that's 1100. And there's no need for them to think about it. I don't do, I do some low level, but I often forget these. 5 is nice to know, the 10101. But as soon as you start knowing how these correlate, you can kind of do that back and forth pretty fast. All right, so far we've put 8 bits together. And this is called a byte. And this basically lets us go maximum from 0 up to 255 decimal. So that's the maximum number that we can store. And that is called a byte or an unsigned char. And I have no idea, well, I think I have ideas why they call it char, but it's not a great name to be calling them because it's kind of confusing. If we want to do things like store a signed integer, if we want to go negative, then we can do tricks like we can reserve one of our bits for a signed bit. Now, it's a little bit more complicated than that because we don't really need to store -0. We can do some other tricks. It's really neat how they do it if you've never seen. But it's really neat kind of how they do the negative numbers. But this is, signed integer. If we reserve one of those bits, we can now do -128 to +127. And this is called a signed byte or char. And it's very important when you're writing computer programs to realize what size of data type you're using. Because the overflow has caused the death of many computer programs. And the number of bugs that overflow has caused is probably not at infinity, but it's probably approaching infinity. Like it's that high. So just be very aware of what your maximum size is. If we want to go bigger, we can put 2 bytes together. So we have 16 bits. Again, this goes up from 0. 65535 is the maximum. This is called a word for some reason. That's kind of a Microsoft. People kind of grabbed that for a standard. It's another strange name, or an unsigned short. I'll probably be using short for that more. And again, you can have a signed word or a signed short that goes from -32768 to 32767. And then, of course, if we need to go up to bigger numbers, we have a 32-bit signed integer. And this is all the way up to 4 billion. 32-bit signed integer go all the way up to 2 billion. Now, an interesting story is that back when they built YouTube, they had a counter for YouTube. And they built it, the counter for the number of views, and they built it as just a signed integer. But as they thought, who in the world is ever going to have a video that gets more than 2 billion views? Come on, there's only 8 billion people in the world. Now, does anyone know the first video that broke the 2 billion view mark on YouTube? Anyone know that?
I think I know this one.
Okay.
I think it's Weird Al Yankovic with his Amish Paradise.
No, it's not.
Oh!
Close. Yeah. Yes.
Is it Gangnam Style?
It is Gangnam Style. It's the old.
Wow.
It's the old Psy doing this guy. That was the first one, and forced YouTube to go and completely change all of their counters to use this glorious number, which is 64-bit integers, which you should use as much as you possibly can. That will get you up to 18 quintillion. And now if we keep watching Gangnam Style at our current rate, which I think we probably will, then we probably have about, I think it's 4 quadrillion years before we're going to overflow this. So we have a long time before we're going to overflow the 64-bit integer. I think we're going to be okay for a possible.
Everybody should watch it as much as possible.
We should try to watch that. We should schedule that in to keep going. Okay, well, mission, we'll make a pact. Okay. Now, this is just a huge number. This is, it's hard to fathom how big 64 bits can store. The amount of data that they estimate ever created in the world is estimated as 2 to the power of 68. So it's not much higher than 2 to the power of 64. So it's just a huge number. So 2 to the power of 64 is going to do most things. Those integers are great, but what if you want to store floating point numbers? And then we have to do some more tricks. Then we get into some other standards. We start stealing our 1 sign bit. We start stealing 8 bits for an exponent, and then store 23 bits for a fraction. Again, this is a standard, and this is built right into your processor. Your processor knows how to do these numbers. It knows how to do them incredibly fast. How many millions or billions of calculations it can do. But the precision of these floating points is only about 7 decimal digits. You have to be very aware of that. So even when you're assigning a big number to these floating point values, you may not read back the same value as you assigned because you're losing precision. So they have a 64-bit floating point number, and these are incredibly common, and you should use the 64-bit floating point numbers as much as you can, and that's getting you up 10 to the power of 308, and that's about 15 significant digits. All right, so how do we store characters? We've kind of got into numbers. We basically need some kind of standards, and I'm sure everybody's heard of ASCII. And this is basically a standard where somebody came along and decided, let's see, hex 41 is going to be equal to A. Congratulations, that's your number you're assigned. B is assigned to 42. 50 is assigned to P. You're going to remember that. I'm going to ask that again in a few minutes. 50 is assigned to P. Let's see. So this is standard. This only uses the first 128 bits of the byte. Now the thing is that ASCII is very limited. That's just your regular letters. So if you want to do anything international, then you run into a huge number of problems, and there's all these other text character sets, and I don't want to talk a whole lot about them because they can be very annoying. But you have ASCII, and then you can add in the upper range, you can add in other character sets. You can do Greek and Hebrew, Vietnamese, in those kind of top 128 to 255. There's other good standards that you should be using. UTF-16 that has 2 bytes per character, and even that is not enough to store all the characters that can be displayed. UTF-8 is becoming more and more common. And it's becoming kind of much more of a standard. And it has multiple bytes per character, so it usually has 1 for simple text, but then it can go up to 2, 3, and 4. And then there's a whole bunch of other text character sets. So basically, we just need some kind of standard to go from some binary value to some text character. All right. Now, we want to talk about endian. So if we have a big number, we have a 32-bit number here, and now if you remembered you're converting from bits to hex bytes. We have 0000001, that is a 1. We have 1010, that's equal to an A. 0101, that is equal to a 5. 0010, that's a 2. And we've got a C at the end. So that is a nice 32-bit number. Now we want to store that on disk. Now there's the obvious way to do that, where we split it into 4 parts, and we drop it on a disk, 0000, 01, A5, 2C. But there is another way to do it, which is not obvious, and at first glance appears quite annoying, is that we reverse the byte order. So we write the smallest one first, 2C A50100. And there's two different ways of doing this, and each one of them has pluses and minuses. And this is kind of like one of the big format wars where there was two ways of doing it that were competing. And when I was growing up, 20 years ago, there was a bunch of big endian processors and a bunch of little endian processors, and they were kind of fighting it out. And it was kind of like one of these standard wars. Like, anyone remember the Betamax war? Do you remember who that was with? Anyone know Betamax versus VHS? Thank you. That's free software. Or anyone know more modern HD DVD? Had a format war with?
Blu-ray.
Blu-ray, very good. So this was kind of like a format war that was going on, but the general public doesn't know about it. It was only us computer science people who kind of knew it was going on. So anyone know who the winner was? Who was victorious? Yes. Little endian has become victorious. And almost all computers these days, including Windows, even the Mac ARM, everything is becoming more and more standardized to little endian. And there's reasons for it, and there's kind of technical, and I don't completely understand it. I think it's about how you can cast things. They even store this inside memory. This is not just on disk. This is inside the CPU. So there's cases where it's easy to cast from or basically convert from a 32-bit integer to a 16-bit integer back and forth without doing any work. Where in big endian, you've got to shift things around. It's kind of complicated, but it's a very interesting thing. Now, did anyone, this is a tricky one, and I did not know this until last year. Does anyone know where the term endian comes from? That is tricky. Yes?
The actual transistors which are used to do the operations.
The endian? No, okay, I'm talking about the actual name, little endian and big endian, where okay. Because I didn't know until a year ago, and I was quite surprised. Anyone know where it came from? Okay, it has absolutely nothing to do with computer science. It has nothing. It is Gulliver's Travels, that's right. Get this guy some free software. In Gulliver's Travels, there was the Lilliputians, and they had a war in it because there was two sects of them, and one of them would have their hard-boiled egg, and some of them wanted to break it from the little end in, and some of them wanted to break it on the big end, which is the big endian, and they went to war. So it's basically a term that there's two ways of doing it. Let them fight it out, and why they, it was just a kind of a funny term that they use, funny term that you get in computer science. My last note about endian is when I worked at IBS, we did a bunch of interviewing, and I helped the boss interview a bunch of people, and my boss's, one of his first questions was, can you explain endian? And some people could come in and explain it dead on, and some people had a degree and had no idea what endian was, and the boss just kind of dismissed them very late. So who knows, maybe this presentation will get you a job someday. If you I understand what endian is, I understand it's the byte order that you've got to worry about, might get you a job. All right, so let's move into, we kind of know the basics, and we want to get into what a hex editor is. So this is a hex editor, and it's got three areas. The left column is the address column. The central area is called the hex area, and the right side is called the character area or the char area. And this left area lists the byte address of the first byte on that line. This hex lists every byte, 16 bytes all in a row. All right, now, can anyone remember I told you to remember what the hex 50 was equal to? Can anyone remember that? Yeah, my cursor kind of showed that. So it was equal to P. So here we have the same hex bytes repeated, but now we convert it to a character set. And the character set you can choose on this right-hand side to be any kind of character set. I think this is ASCII plus ANSI, which is another one. So this is basically a whole line of 16 bytes per line. Addresses, hex, and char. All right. Now, let's see. So I am going to show you a little bit of the software. So this is basically O&O editor, 010 editor, and this is the software that I've written. This is basically a hex editor, and it works, basically like a text editor. You can type into it, and you can overwrite characters. You can, type in, change things around. And you would be amazed at how many hex editors can't even do that properly, that can move a cursor around and just insert bytes and modify bytes properly. It's amazing how many pieces of software mess that up. So here, if I select a set of bytes over the left-hand side, the corresponding bytes on the right-hand side are selected as well. So now we can see, before we saw the file 0001.txt, and we can still see that. But really, you're going to argue that we're not really that much further ahead than we were. We looked at this file back in Notepad, and it's still kind of gobbledygook. We still can't really understand what is going on. Now, we can kind of try to look through the file. Now, we have what we call an inspector over on the right-hand side. And this allows you to interpret bytes in different types of data types. And we're going to kind of look through and, okay, so if I select those 4 bytes is equal to the signed integer of this number. And you can basically, interpret data using all these different formats, but it's really, really difficult to figure out what you're doing. But hex editors do have some uses. And I talked about I like to edit some save game files. About 6 or 7 years ago, my son was playing, it was a fishing simulator game. And he only had a few credits, and he wanted to buy the biggest boat. And my son, who was 6 or 7 years old, didn't have a whole lot of patience to make it up to the millions of credits that he needed. So me, being a good dad who writes hex editors that I am, loaded it up and found out that he had, I think it was, let's say 13,622 credits. So I saved the file, loaded up the save game, and then you can just do regular things, like you can do a search here. Now this is kind of beyond just a regular text editor, so I can search for all these different data types. I can search by sign short. So let's search for an integer 136, and I found that. And that is because this is a presentation and this is a setup. So I can go over here, yep, see there's my 1,622, so I can edit that. Let's give you 5 million credits, save the file, and load the game, and you're done. So that is how you can go through. You can use hex editor to do things, and companies think that because, we have data in binary that nobody's going to be able to edit it, and that's because working with binary data is tough. But if you know what you're doing with one of these editors, then you can kind of get through.
Can I link this to my bank account?
You may get in a little trouble. All right. So let's go back. So the hex editor, the main problem with the hex editor is that it really just looks like a hex editor. It doesn't really display that much more information than we need. So we need something better. And I want to talk briefly about Fledermaus. And this was the company, IVS, that I worked for over in Fredericton. And this was ocean visualization software. And this software was kind of on a different level than I had been used to working on before. This software was about 20,000 Canadian for a single license. So every time you sold a license, that's a pretty good car. So this is pretty high-end software. But it was being used by big research vessels who would be going out and spending millions of dollars on equipment, and then $20,000 wasn't that much more. So basically they were working on surveys of ocean floors. And basically, if you had a harbor and strip away all the water and want to see what the ocean bed looks like, it was really interesting work. And let's see, I've got a little video here, and I can play that. It just kind of show, we don't need sound here. All right, let's let that play. It just shows some of the things. So it was basically ocean floor work. And a lot of this data would have been collected with a towfish. Does anyone know what a towfish is? Anyone have heard of one? No, it's probably not that common. A towfish is basically like a giant torpedo that you drag behind a ship. But instead of having a payload, it's got a whole bunch of sensors. And as it's going by, it's pinging down and it's reading back data from the ocean floor. But it's reading back huge amounts of data. And they will go out on these surveys and go out for 4 months, and they just call it mowing the lawn. Well, they'll just go back and forth over an area and just sweep back and forth. Kind of boring work when you get out. I never went out on the ship, so I was much more kind of developing the software. I'll play that again.
I actually know somebody who built those things.
They built really?
They built those,
okay.
those tow-behind sonar
Was
things.
it on PEI? There are?
No, they
Okay.
were over in Bedford.
Oh, okay, yes.
I think he might be sitting over there, built circuit boards for those things.
Oh, okay.
If I remember correctly.
Okay. Oh, very good.
Is that right, Dr. Sweet?
You did some
Yeah.
ocean. You did some ocean stuff.
Yeah.
Yeah. So it was really interesting software, and I've even turned on CNN and seen kind of the software on CNN and seen kind of the code that I had written to do renderings like on CNN. I picked up a National Geographic one time, and it was a big spread, and it was all the software they had written on. I was like, this is all my, I can recognize my rendering code. This is kind of neat. So I had a really good time with Fledermaus. And that was, by the way, that was a sub that was sunk off New Hampshire. I think that's where it was. So let's go back here. Now, all right. So now, question: does anyone know where the name Fledermaus came from?
German.
It's German. Do you know your German? How good is it?
It's a bat.
Bat, very good. Okay, so someone had the bright idea. We had a 3D input device that allowed you to make 3D movies that you were flying, through a scene, and it was basically like a mouse, except it was a flying mouse. So a flying mouse, somebody had the smart idea to call it a bat. That's a little computer science humor, I think. And then they just translated it into German, which was Fledermaus. There's also a famous opera, Die Fledermaus, I think. So now I was working on one of these big data sets, and we were, keep getting in these giant data sets at Fledermaus. And I had a problem. You're processing this big data, and then I would get spikes in the middle. And now that is a major issue because if you have a ship traveling along and there is a shoal, they have to mark that on the map as being a navigation hazard, so it's very strict. So you have to know whether that is a real spike or not. So I wanted to go in and look kind of at the raw data that they gave us. Now the raw data was this huge binary file. And I wanted to take a look at the file. I could even kind of use a debugger. I could tell, approximately in the file. I think I knew very close to where the sound was individual point measurement was causing these spikes was a problem. But I had no way to really look into the file. So what did I do? I said, there's got to be something online that I can check out this. So I download a whole bunch of hex editors, and thinking that it's going to be, a 10-minute job. And nothing out there could even come close to what I was interested in. Some of them could apply, a few data types to a certain area, but nothing could even come close to helping me figure out where I wanted. And then it's like, this is good. I can't stand this. I'm going to have to figure out how I can dig into this binary file and figure out what the problem is with this data. All right. So now binary data formats. Now this was, the binary data format I was working with was called a HOF data format. I think hydrographic something format, oceanic format. So each sounding had a whole bunch of different things, and this is kind of a standard way of representing a data format. They have a data type, int64, and then basically the name or what kind of data it stores. We have 2 shorts, a bunch of chars. Remember, that's just a single bit. The shorts are a single byte. Shorts are 2 bytes. Doubles are 8 bytes. All right. So how do we represent data formats? Now, a common thing is, and this has been done before, is to turn this into a C struct. So we basically take all these different data types, put a semicolon at the end, wrap it in a C++ struct. And that is useful, and that some other software has done that before, and you could take a struct and apply it at a certain place. The problem is that that's not really powerful enough to do the format that I was looking at, because some of the formats were variable. Some parts, they changed depending upon what data was in there. So I kind of racked my brain for a long time. How can I get into this data? How can I process? How can I figure out what it is? And I finally came up with this, and this was kind of the eureka moment for me, is I put an if statement inside of a struct. And this is something that I had never seen before. I've heard of one guy who claims he came up with it before me, but I've never seen any proof, and I don't know. But this is about 20 years ago I started doing this, and I had never seen it before, and it looks kind of strange at first, but it actually turns out to be very useful for identifying for data formats. So basically, we've got a HAPS version up at the front, and it reads through, and then you look at that value of the HAPS version, and that can tell us what other data is in that data file in that struct. Now, if you know computer science, it might take you a while, and it took me a while to figure out that this is a whole lot different than this, okay? This one is like a regular C struct, and C compiler can figure out the size of everything at compile time. This one, you can't figure everything out at compile time. You've got to do it at runtime. Okay, you've got to do it when the program is running. So this becomes much more like an interpreter, if you are aware of kind of interpreted languages versus compiled languages. Okay, so this becomes much. So I started to look at some other ideas of what kind of could be done with this kind of system. So if you had, a struct, if I had a header that had the number of soundings up here, and then I had another struct with a sounding, and those become data types, then I can declare variables just like in C++ or other languages. I can declare a header, and then I can declare a sounding with an array using header.num soundings. All right, so this is kind of a neat way of reading data from these different structs. And this was kind of when binary template language was born. And this was kind of the eureka moment. And I had, well, when I was working with Fledermaus, we had patented some ideas. We had spent a lot of money patenting. I had brief thoughts on whether I could patent this idea until I realized how much I actually detest software patents, so I never went out and did anything. So people have kind of copied this online. You'll see there are some kind of free tools around there, but I still think this is probably the best tool out there online. It's certainly the most well-known that works with this kind of structures. So a binary template is basically looks like C and C++ structs, but they can contain if, for, while, and switch statements. Again, this is interpreted, so you've got to do it step by step as you're going through the code. The file extension .bt, and these are meant to be read-only, which is kind of important. So I want to send my binary template to somebody else. They can apply it on their data, and there's no worry about that doing anything to their machine. It's just kind of read-only. I want to analyze this. And this was, this is as close to ANSI C as I could get it. I still like ANSI C for doing low-level editing. I find that still kind of the most useful program. Let's see, where am I going? Okay. So one of my problems was I didn't really know how to develop a language, and I had gone through and done a master's and never really took any computer science languages. I kind of avoided them like the plague. So if you are doing computer science, I encourage you to at least take some languages, at least understand some EBNF forms. I'm always dealing with shift-reduce conflicts, which drive me crazy. If you can explain to me shift-reduce conflicts, I'd be happy. But yeah, languages are very tricky, and it's very good to have kind of a better understanding than I did going through. I grabbed an old copy of Yak and Bison, which is basically a way of doing EBNF grammars, and developed that and made my own language. Because this was a totally new language. This was not based off C++. This is a totally new thing. So I just want to just kind of cement this in how this works. So if I have a struct header and I have a char and a type4, that's going to map to the first 4 bytes in that file. Okay? So type becomes an alias of those first 4 bytes. So if I want to read the value from disk, all I have to do is access this variable type. If I want to write to that spot on disk, all I have to do is assign to that type of variable. So these are kind of special variables that map to disk now. All right. So what do we do kind of after we run a binary template is we display things in a hierarchy. And it's basically an expandable tree. And I'll just show this. So if we go back to our sample zip, and I'm going to run. Okay. So down at the bottom here, so let's see. So for the first time, we now have a zip file, and now I can see some of the data that's inside of the zip file. I have a version here, which is 20. I have flags. I have compression, which is 80. And I have file time. I have a file date. I can actually go in, and if I want to, I can edit the file time inside of a zip file and say, no, this file hasn't been touched since 1994. You can do all kinds of tricks with that. But there's not much security in zip, so you never trust zip. So you can see compressed size here, compressed size and uncompressed size. Now, if you can see when I go up to the top, these variables kind of highlight, so you can see the individual variables. And when I let my mouse go for a second, it actually shows you a pop-up. So if I want to see what that 8 is, that's method deflate. Let's see, that 56 is uncompressed size. The 52 hex, that's the uncompressed size, is 82. Does anyone notice any problem? Another question. Anyone notice any problem with the compressed size and uncompressed size? Any problem? Any problems? Hint?
Oh, the size of it?
The size of it. It's only 32 bits. Yeah. Because nobody's ever going to want to store more than a 4 gig file in a zip file, of course. And of course, they run into that. And so then, of course, because zip wasn't built for more than 4 gigabyte files, they had to add another extension called zip64 into zip, which is an actual hack. Which is absolutely horrible, and I won't even display it because it's so ugly. But just a horrible hack of a format. So basically, you can browse through and see all the different parts of the zip file. You can browse, basically see all the different parts of it. Let's see, we're going to go back. All right. So let's go through. So we just add a few features here that are kind of built into the binary templates that allow us to handle the more complex data. We can have little functions that you can put in, like little endian and big endian. So you can actually have some data formats have mixed endian. Some will have data that is in big endian and little endian, allows you to switch back and forth. Very annoying. You can apply colors to things. It's very nice to be able to put a color on a certain section of data. If I want to do things like use a regular keyword that's not mapped to disk. I have a local keyword, so I can, if I want to do something with a float, like an I counter, I can just declare local int. And you can, some data formats you'll run into have data that's even out of order. It's not in any particular order. So there's got these ftel and fseek functions. You can kind of jump around. And another thing that you can do is you can actually pre-read data. There's these little functions called read in, so I can read data. In this case, I'm reading a tag from disk at the current position, and then depending upon which tag, I can create different types of structs. It's kind of a neat little way it's used in zip. Some other little handy things, there's what I call duplicate arrays, which is a neat little innovation that if you declare a variable multiple times, like int x, int x, int x, usually that's invalid. That will give you an error in C++. In this case, that creates an array, which you can access with x0, 1, and 2. Then you can do nice things like this, which says while you're not at the end of the file, keep defining records, and that will make you a nice big array of records. So it's just a very fast, kind of slick way of reading through data. So just trying to make these templates kind of flexible, and this has been added over time where people said, your data, your binary template can't handle this format. Can you add this to it? How can you handle this? And it's constantly going back and forth. And I'm still doing that. I'm still fighting with handling different types of data. You can even create your own custom variables. Right now we've been dealing with regular variables. For example, this variable is 16 bits, but it's got 8 bits, and then a period sign, and then the 8 bits on the right side. So it's basically a really small floating point version. I think they would use it in something like Quake. Did that. Yeah, you can do read and write functions with those too. That's good. Again, I said that these templates were meant to be read-only, and that's been on purpose so that people can share them. If you do want to do editing, there's a nice feature called scripts, and then you can actually just assign to those variables that we have. So this is a thing that goes through. If there's a bunch of salary records, we can iterate through them, just give everybody a raise. And I want to talk, one of the neat things about the software was the introduction of the repository. So basically, I made a repository of these binary templates and started putting up online. Now, the software itself isn't open source, but I've kind of made this repository open source where anybody can contribute to it. And right now, I think it's at about 250 different formats. It might be more than that, 260 or 70. So people keep coming, and I've developed probably about 30 of those, and a bunch of people from around the world keep doing their own data formats. So basically, if I have a data format that I make, if I'm working with, for example, like AVI files or an MP3 file, if I make a binary template that allows me to understand all the data in that file, I can upload it to the repository. And then periodically, everybody's software in the world will download the tags from this repository, and then they'll instantly have access to that template. So as more people use the software, the hope is that it becomes more and more powerful. More people are using more formats. It's becoming more and more useful, and it is getting, it seems to be increasing. More people are using it around the world. Let's see, where did I want to go? So let's go back here. Let's just go for a second. I just want to show the zip template for a second. So I just want to show you very briefly what the zip template looks like. So this just looks like a regular C++ program. Let's see. Yeah, so you can see we've got a bunch of different variables. All right. So we're getting a little bit. Are we getting a little over time? Little tiny bit over time. Not by much. Okay. We'll try to wrap things up here soon. let's see. So let's move back into, I'm going to skip some of that. So I can show, people are interested, I can show a bunch of different data formats. I was going to show BMP and zip, or there's, MP3, there's, yeah, I've got a bunch of different data formats. If people are interested in kind of what's inside of them, I can actually show you. Let's go back. Now, large data is kind of things start to fall apart when we deal with large data. And things become much more difficult when we're not talking about a gigabyte data set. We're talking about 10 gigabytes of data or 100 gigabytes of data. We're talking about these giant data sets. So basically, I made this thing where it's kind of a virtual file table that you can basically store blocks that are on disk or on memory, and the blocks can be variable sized. So when I load up a giant file, I only need to load up the first little section of the file, and I can leave the rest on disk. And it's basically a cached version. I only need to load in what I need to as I go. So, it comes when you want to insert data, usually I could take a giant block, cut it into a little bit, and just expand. There's a few neat innovations for large data. For example, my big HA file that I was dealing with had about 10 million records. Now, 10 million doesn't sound like that much, but if you're talking about 100 bytes per record, you're talking about over a gigabyte of RAM just for that data structure, and that is a lot to really slow down your computer. So there's a neat little optimization you can do. Basically, if you know that all of these structs are exactly the same size, you only have to allocate one. And then you can basically just use that one and use it as an offset into the file, and you can basically just make an accessor. It's kind of a neat trick. Now the problem is if you have variable size structs, what do you do then? Basically, I've got the struct, but I want to skip over it. And it comes down to basically is I want to know what the size of that struct is. I want to skip over it so I can get to the next struct to get to the next struct. And now the thing is that we realize that you don't have to allocate the full struct. You can only have to allocate the very top level. You can leave out the rest. And as long as we know what the size is. So then we come up with this little thing which is using a size attribute. So here we write a size function. And this goes back to our little read uint and read ushort functions. And this allows you to basically skip over a large section of data. And this turned out to be one of the most useful things for working with large data. And I want to go back and show you one. So let's go for big data. I'm going to load up my full C drive right now. So this is 993 gigabytes right now that I am loading. This is basically the NTFS file system. I'm going to look through here. This is basically the root directory of the NTFS file system, and a lot of these are hidden, extremely hidden files that you would never find in Windows. You can, I think you can browse into some of these. We got data. Yeah, I can take a look at some of these data. Yeah, this is some data that is not public by any means, or not supposed to be. You can go through. So I can even, I had some files down here in temp. I had even some files that I stored on disk earlier on in the day. I had 001.bmp. I can open up that file. Let's see, okay, data is here. I can look at data. I can drill down. Yeah, it's okay. So there's the data. So that is a BMP file. I instantly jumped to that BMP file. And that is even the slack space. If you've heard of slack space after a file, it's basically the data left over after is allocated on the file. So this is basically your whole hard drive that you can browse through, and you can see this is fairly responsive. You can still scroll up and down and scroll down through. My only bigger thing I can do is open the whole logical drive. Let's see, which contains actually, okay, we've got the EFI. So we have 6 partitions here. We have a hidden system partition. We have the recovery partition. What's in the recovery partition? Yeah, you can take a look at all these hidden system files. So basically, there's 6 drives, and you can browse through this and see it very easily. So I'll show you briefly. Maybe it's just easier to show some of the visualization on the right side. You'll notice that. Well, let's go back to examples. Let's just go zoom. So we want to do some visualization too. And there's been this concept of doing just a mini map, was basically having a little table on the right-hand side, basically in an editor. If I get back to this, yeah, this is kind of a mini map that shows you basically the code outline. So what does that look like for a hex editor? And I don't think I've seen anyone else do that. So this is kind of a visualization tool on the right-hand side. You can control through. So you basically, there's a bunch of different techniques that you can apply. Colors. Yeah, there's different ways you can colorize these things to get different effects. Really, this is probably the most interesting. You're basically doing a blended version. So here, if you're doing visualization, you can see that this data down here is all modelly. So that tells you that this is actually random data. So that's most likely compressed. Now this data here is very smooth. It's a gradient. So that is most definitely not compressed. In fact, it's just this gradient. Now data in the top here is not kind of squiggly. It's just kind of yeah, a bunch of little random pieces here and there, and that is the actual data. And once you get to recognize, you can kind of tell where the data is in your file. And there's things like even exe files are very interesting when you start scrolling through here. When you start, yeah, there's lots of interesting things when you start visualizing an exe file. EXEs are just kind of crazy how much work they put into exe. Let's see. So we've kind of covered some of these things. Yeah. So in the future, I'm looking to expand the templates. It's got to keep working. We got to handle more different types of data. I'm wondering whether to open up binary templates, because right now they're just used for this product. But should I allow other products to use it, and should I do that for free? Should I charge people to do it? I don't know, and I'm open for feedback of those things. I'm looking at adding in more IDE features, like there's a neat code parsing library called Tree Sitter I'm looking at right now. There's a bunch of other things. So again, if anyone wants free software, you can email me, gsweet@sweetscape.com, or go to one of the websites. I mentioned in kind of the abstract about talking about business things. If anybody's interested in that, please come and talk to me. And I think we'll end that for now. So is there any other questions, or do you want to?
Yeah, let's thank our speaker first. I'm sure there will be lots of questions. We can do most of that over pizza. Sure. But let's do one or two right now. Does anyone have a question for our speaker? Yes.
Do Hamming codes factor into binary data analysis at all?
The Hamming codes?
The self-correction codes.
The self-correction codes. They could be built into templates. It's not. They could be written in templates using coding, but it's not built into the language itself. But you could do the Hamming codes, and I think there are some people who have done that with their own code. Okay.
All right.
You want to do that?
I have been told that the pizza is ready.
Okay.
So let's thank our speaker once again. Again, we have such a big crowd, we should have enough pizza for everyone to have a slice. Please be patient for everyone to have a slice before you go back for a second, and there should be a can of pop for everyone. So let's go to the third floor pass.